Example 2. R of x equals x divided by x minus 1 times x plus 2. So let's look at the domain first. We're going to set that denominator equal to 0 and find the excluded values. We can actually read these because R of x is already in factored form. So we have the excluded values of x equals 1 and negative 2. So in interval notation, from negative infinity to negative 2, jump over negative 2, travel to 1, then jump over 1, and then you can go on forever to infinity. And also, by inspection of R of x in factored form, we have no common factors between numerator and denominator, so we have no holes. Remember, that's no common factors. So we didn't have to do that work because it was already in factored form. And then also by inspection, we have 2 zeros of the denominator. We don't have a reduced form. R of x is just going to be R of x, so we'll use that throughout the rest of the analysis. So we have a vertical asymptote at x equals 1 and a vertical asymptote at x equals negative 2, because those are the zeros of the function, and we didn't have any holes. So they're both vertical asymptotes. Now for horizontal oblique, well, we're going to have it horizontal because the degree of the numerator is 1 less than the degree of the denominator. In other words, the degree of the denominator is greater than the degree of the numerator. So look back a couple pages and we have that case. We have y equals 0 as a horizontal asymptote. Now we might want to see here for the first time, well, does this graph intersect the horizontal asymptote? So we have to see what solves this equation. Well, let's just solve this. Solving this, you can just say, well, what would make this 0? Well, x equals 0 would make this 0. So we do intersect the horizontal asymptote at 0, 0, so at the origin. Now for the intercepts, for the x-intercept, we plug in 0 for y. So 0 equals, this is kind of the work we just did, right? We're doing this again from like the step before, but for the intercepts. So this would imply that we get x equals 0. So we have an x-intercept of 0, 0. And also that's our y-intercept. But if we did the algebra for the y-intercept, we're just plugging in 0 for x. So y would equal 0 over negative 1 times positive 2, but that's still 0. So we came to the same point. So the origin is both the x and the y-intercept. Now, when we're going to graph this with this information that we have so far, so you'll have to look on your paper, I'll go ahead and put in our asymptotes. And we only have 1 point, so we're going to have to do a little bit more of an investigation here. So at x equals negative 2, I have a vertical asymptote. Also, at x equals positive 1, I have a vertical asymptote. The only point that I know so far is the origin. So I know the branch that's between x equals negative 2 and x equals 1 will have the origin, and I also know that that origin point on the graph crosses through the the horizontal asymptote of y equals 0. It's not a lot of information for knowing how this function looks, so we're going to have to pick some points. So let's pick a point to the left of x equals negative 2 and figure out what that is. Let's find r of negative 3. So we're going to have negative 3 over negative 3 minus 1 times negative 3 plus 2. So that's going to give me negative 3/4. So at negative 3, negative 3/4. So I'm somewhere around here. Now, when this point, it lies below the horizontal asymptote and to the left of x equals -2, that vertical asymptote, and it's bound by them. So I do a branch that looks like this. Now around the origin, I'm going to pick a point, pick an x value to the left of the origin. So maybe I'll pick -1, r of -1. So I have -1 divided by -1 minus 1, -1 plus 2, and that equals -1 over -2, so that's 1/2. So I have -1, 1/2, so I'm about here. I also don't know if that will jump back up yet or not, so I'm going to pick a point just to the right of the origin as well. So I'm going to pick +1/2. Now I know we don't like working with fractions, but I just really want to see about where this falls. So I'm going to have 1/2 minus 1 here and 1/2 plus 2. This is going to end up being, let's see, 1/2, -1/2, we have -2/5. You can check that with your calculator if you need to. So I have 1/2 and -2/5. And now I have 3 points. And I know I'm stuck between these two vertical asymptotes, so it's going to look like an S-curve. So, because I know I intersect the horizontal asymptote at the origin, so it looks something like this. I lost my little point there, but that's okay. And now I'll need one more point, because to the right of x equals 1, I could either be up above the horizontal asymptote or down below it. So let's see where we are with just one single point. So I'll pick 2, because that's a nice easy number to work with. I'll have 2 minus 1 in the denominator and 2 plus 2. So this will be 2 over 4. That will be 1/2. So at 2, 1/2, I know I'm above the horizontal asymptote, so this branch will be confined between the vertical asymptote x equals 1 and the horizontal asymptote y equals 0 and above that, so it looks something like that. And again, that's just a basic and rough sketch of the whole function. Now our end behavior. So first, our vertical asymptotes. As x approaches 1 from the left, f of x approaches -infinity. As x approaches 1 from the right, f of x approaches +infinity. Now let's go to the other vertical asymptote. As x approaches -2 from the left, f of x is going to -infinity. As x approaches -2 from the right, f of x is approaching +infinity. Again, look back at the graph and make sure that you understand why these two pairs are written the way they are. Now for the end behavior, we know we have a horizontal asymptote of 0. So as x approaches -infinity, f of x is approaching 0. It happens to approach 0 from below. And as x approaches +infinity, f of x is also approaching 0. It's just approaching 0 from above. And that was a pretty long example. We'll do another one in the next video.